Okay, so in this lecture, we're going to introduce a new type of integral. We're going to be integrating vector fields here. So let's go ahead and recall something we've done before, which is consider work. So recall back when we were doing dot products, we had a vector force F, and we wanted to move an object to displacement vector D, then the work was just given by the dot product of the force with the displacement vector. In this situation, the force vector was a constant force, and the displacement vector was just a single vector in one direction. What we're more interested in doing now, though, is we want to consider a force that's a vector field. So the force can change for different points x, y in the plane, which is more realistic. We don't want to always have to have constant forces. And the other thing we want to talk about is, well, we don't want to always have the object have to move just along a straight line by a vector. We want our objects to be able to move along curves so they can take vastly different directions. So we want to figure out, we're going to use this first formula, the F dot D, and we're going to use that to figure out how can we calculate force with a variable vector field force and moving along a curve. So the first thing we need is we're going to need to consider oriented curves. So an orientation on a curve is just we're going to choose a direction to travel along the curve. And any curve with a chosen orientation is referred to as an oriented curve. So to see this, here we have a curve C, and notice we have an arrow on this curve. So this would mean we'd start towards the left down here, and we traverse the curve in the direction of the arrow. So that's an orientation on the curve. So it tells us which direction we're going to traverse the curve in. So now what I want to do here is let's start by just moving a short distance. So I'm going to take an object, and it's going to be at some point P1 on the curve, and I'm just going to move it from P1 here to P2. So just some short distance. Assume these points are close together to each other. And let's figure out if we can approximate how much work is done in moving from P1 to P2. So we want to work with vectors here, so we can consider the vectors that start at the origin and go out to the point. So let's call this one R1 and this one R2. So those are our vectors that go from the origin to our 2 points that we're working with here. So we start translating this into a problem with vectors. And now I want to traverse from here to here, and we can see that's approximately given by a vector. Namely, if I look at the displacement vector here, delta r, we're going to define that to be r2 minus r1, which is the vector from P1 to P2. And we can see it's not exactly the curve. The curve here is in the blue, and the vector doesn't exactly go along the curve, but it's a pretty good approximation for the curve. And the closer P1 and P2 are together, the better that approximation will be. So we can go ahead and say, well, I know how to move along a vector, and so we can approximate the work as follows. We're just going to go ahead and instead of using the curve, we're going to assume the force, as long as P1 and P2 are pretty close together, the force won't change too much over that displacement vector. So that should be a FR1 dot delta R there, not dot R1. And so this here should be a delta R1. And so when we do the work that we saw at the very beginning, if we have a constant force moving along a constant displacement vector, it's just the dot product of those. So the work moving along the curve is approximately the force, which we're just going to say is approximately constant. It'll just be the value at R1, and then dotted with our displacement vector here. And that gives us an approximation. The closer P1 and P2 are together, the better the approximation will be. Okay, so this is a way we can approximate the work done moving along a small part of the curve by a variable force. Now, obviously, we want the total work. We don't want to just be able to move between 2 points that are close together. We need to still be able to move along the entire curve. So what we're going to do is we're going to take that curve and we're going to break it up into a bunch of little pieces using, say, n points here, where n can be some large number. And then each of those points comes with a vector from the origin to the point. And so the entire curve will be broken up by P1 to Pn. That'll partition the curve up into pieces. And now we know moving from P1 to P2, we can approximate that work. Moving from P2 to P3, we can approximate that work, and so on and so forth to get the works along each piece, and then we can just add all of those up to get the total work. So W total is the total work to move along the curve. And notice this here is the work to move from PI to PI plus 1. And so we're going to go from I to N minus 1 here. And this will give us the work moving along each segment. And then we add all of those up to get the total work. So notice here replacing the delta Ri with the actual difference here to see what we're working with. So this is taking that nice smooth curve and approximating it with a bunch of different lines coming from those vectors. And that gives us a pretty good approximation for the total work. Of course, we don't want to have to stick with the approximation. We want the exact value. So let's figure out how we would do that. So as we let the PIs get closer and closer together, we see our approximation will become better and better. So the PIs getting closer together means that those displacement vectors, the magnitude of those should be going towards 0. So if we do that, then the total work will be exactly equal to the limit as those PIs get closer and closer together of that sum. And this here should hopefully look familiar from Calc 1 or Calc 2. This looks exactly like a Riemann sum. There you didn't have a vector there, but notice this is still just a number. And this whole thing here is just a function because you're dotting it together, so it's getting rid of the vector. So you're just getting some, for each Ri, you're just getting some number out. So this is exactly a Riemann sum. And that's how we're going to define what we call the line integral. So we denote this as the integral over C because we're going over a curve C. And it's f dot dr, the vector field, and we dot it with the taking the delta r here and replacing it with the dr for notation purposes, just like we did replace delta x with dx when we were doing integrals in Calc 1 and Calc 2. And it's just the limit of this approximation. So this thing here, this over here is how we define this integral. Okay, so we define the integral in terms of a Riemann sum. And now, of course, we're not going to want to calculate integrals using Riemann sums, and that's fine. We're going to see shortcuts for how to calculate these line integrals later on as well. But right now, we just want to get an understanding of what they're actually doing. So we motivated the definition of line integral by calculating work, but work really didn't have anything to do with how we did it in terms of we could make the same definition for any line integral, any vector field f. Same definition would work. So if we go back here, there's nothing in this definition that said f had to be work. It gave a physical meaning to what we were doing, but we could make this same definition here with any vector field. And similarly, we used the pictures we used were in 2 dimensions because that made it easier to draw, but there's no reason we couldn't do this in more dimensions. In 3 dimensions, it would work just fine. It'd just be a little bit messier to draw, but of course you could also do this in any number of dimensions as you wanted to. You just wouldn't be able to draw pictures. Now what we're going to do is we're going to eventually see how to calculate these line integrals by parametrizing the curves. So we saw in an earlier section how to parameterize curves. This will be one of the places we use that pretty heavily. And we're just going to close out this flipped class video by giving a couple properties of line integrals that we'll use. They're similar to the properties coming from regular integrals that you're used to from Calc 1 and Calc 2. So the first one is let's let C be an oriented curve, and let's take 2 vector fields f and g and make sure they're defined everywhere on C, so you can plug any point into the vector fields and it'll be fine. And we'll let a be some real number. So first thing we have is if I add the 2 vector fields, that would give me a new vector field. And if I integrate that, it's the same thing as integrating those vector fields separately and adding them up. So the integral is additive, just like we saw regular integrals were. And similarly, if I take the real number and I scale my vector field, I get a new vector field. So I could take the line integral of that. Well, that'll be the same thing as if you took the line integral of just f and multiplied whatever your answer was with a. So you can pull constants out front of line integrals, just like you could pull constants out front of regular integrals from Calc 1 and Calc 2. Couple more. If we have C being an oriented curve, we write minus C if it's the exact same curve except for you just traverse it in the opposite direction. So the curve we saw earlier, we walked from left to right. negative of that curve would be walking from right to left. So you just change the orientation in the exact opposite direction. And in that case, if I go in the opposite direction and I take the line integral of the vector field, it's the same as just putting a negative sign out front. So how you should think of this from Calc 1 or Calc 2 is, remember, if we took an interval from a to b and we integrated from b to a, that was the same thing as negative the integral from a to b. So same thing here, you're just switching the orientation here, and it introduces a negative sign out front. And then one last property here, if I have two oriented curves so that C1 ends where C2 begins, and their orientation agrees. So that means if I start at the beginning of C1 and I walk until I get to C2, C2 is going to start where I ended from C1, and then I walk C2 from there. So the orientations agree, so I can make one walk the whole way from the beginning of C1 to the beginning of end of C2. So we're going to write C1 plus C2 for that curve where you start at the beginning of C1 and you keep walking until you get to the end of C2. So if we do that, we can see we can also split these integrals up, this line integral over that sum of the curves, by first taking the line integral of C1 and then the line integral from C2. So this is similar to the property from Calc 1, Calc 2, where if I take some interval AB and I pick a number C that's between A and B, the integral from A to B is the same as the integral from A to C plus the integral from C to B. So same thing here. You can split your curve up into pieces and do the integral over each piece separately, and that gives you the same answer. So those are some of the basic properties. We'll see how to actually calculate these in class and do some examples.